Yeah, I just want to say thanks to everybody for joining the meeting. I think most of the attendees here are resellers, and I think there are a few customers in here as well. So my goal here is to excite everybody about iMachining, and as Emil said, to show why every SolidCAM customer must be using iMachining. And I mean, realistically, every single machine shop should be using iMachining, hands down. It is by far the single best technological advancement in machining that has existed. And it is the software that will allow you to make more money and cut your parts faster. And I mean, outside of buying faster machines, which is huge capital investments, or just adding multiple machines, iMachining is here to save money. It is essentially like adding more CNCs in your machine shop. So, all right, I'm gonna get started and we'll go from there. So, SolidCAM iMachining, as Emil and I said, it is the revolution in CNC machining, and all of our customers are seeing time savings of 70% or more. And realistically, as you're going to see, this is not just for steel and things like that. Aluminum, it is all of our customers that see these benefits. So what is iMachining? iMachining is basically made up of two modules. First is there's a intelligent toolpath generator, and then there is a technology wizard. And essentially the toolpath generator is what a main thing I'm going to go over in today's presentation, because I'm really going to talk about how end mills cut and what they do and why iMachining works so well. And then the technology wizard is actually what drives the toolpath generator. So instead of the end user or the customer trying to figure out all the feed, speed, step overs, cutting parameters for different materials and different tools, the technology wizard does all of this for you. So we package both of these together, so it's a suite that works right out of the box. So first thing I'm going to go over is a couple time savings, because in the end, iMachining is about saving time at the CNC. So and there's a lot of interesting examples here. Like here's a really simple pocket here. This was done with ISCAR at Gardner Aerospace, and this was a simple titanium pocket. This pocket was programmed to be the most efficient toolpath possible in CATIA, and it took 14 minutes for just a single pocket right here. In iMachining, we were able to cut it down to 3.5 minutes. So here was an example of where they optimized the toolpath the best they could to lower the cycle time, and iMachining still came in and knocked it into, I think, less than a third. Here's some savings in aluminum part. So this was a customer who produces electronic components. Most aluminum parts are machined out of billet. So this is kind of not a giant part, standard size part. We see it's got like an 8-inch vise in it. They had 400 pieces to produce. The standard cutting time before iMachining was 17 minutes, and the iMachining cutting time afterwards was 6 minutes. So this is a 65% savings. And this is the end what really speaks the most. Cutting 400 pieces saved 73 hours on the machine. As I said, we've all been there in machine shops where you need to get the parts cut. iMachining is like having multiple machines cutting the same part, but you get to do it with your machine, and it's just a technology module. Here's a tiny little, nothing too big, small little part in titanium, just a simple little bracket, couple drill holes, nothing too fancy. This customer had to produce 75 of these. Standard cutting time was 17 minutes. We lowered that time down to 3.5 minutes. As you see, this is very similar to what we saw also in the titanium part with ISCAR at Gardner Aerospace. So you see a kind of similar time savings. So this went down to 80% savings for a total time savings on 75 parts of 16 hours. It's amazing. Here's another aluminum part. And here, this customer in Germany uses iMachining 2D and 3D. As you see, it's mostly a prismatic, what I would call a prismatic part. It's, there's no really contoured surfaces, but they use a combination of 2D and 3D iMachining. And they, on all of their parts, they see 65 to 75% savings. So you can see the part down here, you can see the part up here. So even customers that are machining in aluminum, and I mean, I come from myself being an aluminum background in the aerospace, most people in aluminum think, I cut crazy fast already. I push my machine to the max. I have specific aluminum insert mills and things like that. We run pretty much almost the maximum of the machine with the feed rates and RPMs. And you think that is as fast a volumetric material that you can get. And the reality is iMachining is faster. And one of the big differences in aluminum is being able to cut deeper. And with iMachining, you put less thermal shock into the aluminum part. So generally, I mean, these parts are pretty bulky, so you're not going to get much, movement in the part. But when doing thin-walled parts, you will see less deflection in the final part after you removed all the material, because aluminum is known when you remove a lot of the material to relax and flex. And the heat that's generally generated from insert mills and high feed, shallow depth of cuts generally creates more heat in the part, and iMachining creates less heat and more efficient cutting. Another major aspect of iMachining is reduced wear on the machine. I would say for aluminum customers, this is a pretty big thing, because most aluminum machining is done at high RPMs, and I think a lot of customers are buying high RPM, high dynamic machines because as I said, most customers in aluminum feel like they are hitting the limits of their machine all the time. They're generally running the maximum RPM. They feel like they are, typing in the maximum feed rates that they can run. So a lot of aluminum customers buy higher end machines, and higher end machines cost more money, and eventually spindles and stuff do wear out. We've had two customers, or two machine builders, Hermle and Makino, both test iMachining against other high-speed machining softwares, and they both have concluded that the cutting forces acting on the spindle is the least amount with iMachining. So this is important, because in the end, spindles cost money. So if you're a customer that's running your spindles around the clock on aluminum cutting parts, even any other parts, but aluminum is definitely the parts where people are maxing out their spindles on almost every single tool, lowering the cutting forces and the spiking of loads on the spindle at high RPMs with these high RPM 24,000 and above spindles, you will gain more spindle life. And spindles aren't cheap in these machines. And generally what we do see from our customers and cutting with iMachining, spindle loads generally range in the 4 to 17% of the maximum spindle power, which in aluminum you can get, we do get higher, but the big difference is we stay in that range the entire time, where when you look at traditional tool paths, you see spindle loads spiking from 0 to 100% and back and forth, because the tool is constantly changing loads. And in iMachining, we just have a constant load the entire time. So I have an iMachining cutting video here, and I'm going to try something I've not done before, which is sharing a video through the GoToWebinar. So I'm going to switch over to that video. Let's see how this works. It's launching up. Now what everybody should see is my screen sharing should have stopped, and now you should have a new, I don't think you guys see my screen at all now. You should see a new window popped up, and there's going to be a video playing. If you like, you can expand this window, because on my computer it does show up as kind of like a third screen. And I'm just going to play this video. It's just a 1-minute video that kind of shows what the
Okay, Anthony, go ahead. It's finished.
I'm sorry, everybody. Sydney just texted me and let me know that when I did the video and I switched over to it, it muted. So hold on 1 second.
No. We heard everything. Anthony.
Okay, good.
Yeah.
Okay. So what did we see in the video? So the main thing we wanted to show here was that in iMachining, you see we do full depth of cuts using almost the full flute length of the tool, and we do high speed machining. So as you saw with steel there, we were running, I believe it was 14,000 or 16,000 RPMs. So with iMachining, you are, in traditional machining, we generally do shallow depth of cuts, and we do lower surface footages. As I said, in aluminum, most people are running the machines at their limits, but in steel, generally you're going to see people running lower surface footages and lower RPMs. With iMachining, we run higher RPMs, higher depth of cuts. So to understand how iMachining achieves this, I'm going to talk about what actually happens in the cutting, because this is the portion where I think a lot of customers and all of us machinists, we've all seen, videos throughout the past, 15, 20 years. You see these, oh, we have these fantastic material removal rates. You see this specific example of a cut, and the end result is they are able to achieve that on a very specific part and a specific machine, but you do not get to get that on your part, on your machines. And with iMachining, we give you that cutting, every part on your machines, and this is how we do it. So there are two main things here with the iMachining toolpath. We work with a variable cutting angle, which ranges between 80 degrees and 10 degrees. And then we also vary the feed to keep a constant spindle load. And I'm going to get more into that. As you can see here in this example, when the tool engagement is less, where the cutting angle is smaller, we are increasing the feed rate in comparison to when the step over or the engagement of the tool is the max. Now I have a pretty cool video here that's called plastic deformation and shearing. And once again, I'm going to switch over to, oh, nope, never mind. Sorry, hold on, okay. Okay, so here I'm sharing this directly through my screen because I want to be able to pause and forward this. So what we are looking at here is, this is not a helical end mill. This is just kind of like a turning insert. So this is the zoomed in video on what is actually happening when material is being cut from a tool. And I'm going to hit play now. And what you're going to see is what actually happens is two things. There's something called plastic deformation, which happens around the tip. So this is where the tip of the tool is meeting the material. And you can see that the metal is actually like plasticized. It's going from being solid to shearing off. And then I'm gonna press play again. And what you see is that you get this shearing effect, and the material is sliding up along the insert of the tool. Now, what's really I find incredibly interesting about this process is, I'm going to pause it right here. You will see that because you're getting this plastic deformation around the tip here, you can see that chunks of the material, the goal here is that all of the material would perfectly be coming up and away from the tool. But what you do see here is you see sometimes the material is actually falling underneath of the tool, and then it's rubbing along the backside of the insert. So what's important here is, and I think everybody has heard this in the machine shop, is getting the tool underneath the material. So when you take a cut, you can't take so soft of a cut that the tool is not able to get underneath of the material and actually shear this. So in aluminum and softer materials, it's obviously less of a problem, right? So like the softer the material, the easier it is for the material to plasticize and then shear away. The harder the material, the tougher this gets. Now this actually makes kind of like a catch-22 with traditional tool paths, because you need to be cutting fast enough and with a heavy enough cut that the tool is actually getting under the material. But if you cut too much with the hard material, then you're actually going to end up in a situation where you're breaking the tool. So I will switch out of this and go back to the presentation. Okay, now I have one other animation. Now this is actually going to be an animation of an end mill rotating and cutting. And this goes back to getting the tool, getting underneath of the cut, getting the tool to actually take enough material that the tool is actually going to be able to shear it away without pushing. Oh, and hold on 1 second. This one I'm going to open up and play frame by frame. All right, hold on 1 second. Enhancements, video settings. Not that one. Playback speed. Okay. So this animation is actually showing the tool in spinning as a helical end mill does, and then the tool is moving in the x-axis and swiping away this material. Now what you see is the tool is actually starting from the thickest amount of material, and as the tool is rotating through the cut, what you're actually going to see is the material is actually getting less and less and less as you go along. Now I'll go to the next revolution. So same thing, we're getting thick amount of material. And what you actually see at the end of the cut, the tool actually goes from cutting 0 material. So if we go back and think about the plastic deformation that's happening here, imagine at some point this tool is going to break out of the cut, and you're going to have this like plasticized material here. Eventually, there's not enough material to be underneath the cut and for it to shear away, and that chunk of material is going to come back underneath the backside of the insert, and where it's actually not cutting at. So this means every time the tool is actually rotating and it's cutting, each flute is actually entering the material and ending the material where there's no cutting. So right there's 0 cutting anymore. So every time this tool is doing this back here, there's a changing of the cutting force. So with iMachining, it's really important that we are managing how much of the tool is cutting. And what we want to do is we always want to go what we call thick to thin. And then the next slide, I'm going to explain a little bit more about this thick to thin. We always want the tool starting cutting the most amount of material and then going to the thinnest amount of material. Okay, so we've seen those 2 animations. So now let's talk a little bit about what I said was kind of thick to thin. So if we take this example of this tool, if we were doing a full slot, what actually happens is at this point here where the flute is first entering the material, you're actually starting with 0 chip thickness. There is 0 amount of material that the tool is touching. So what happens is it's actually taking, depending upon the tool, the sharpness, the material, and everything, it is actually taking some distance before the flute rotates to where the tool is taking enough material where that plastic deformation and shearing is actually happening. So this is what we call climb cutting versus conventional cutting. So when we do climb cutting, we're actually starting from the thickest part of the chip and going to thin. If we're doing conventional cutting, we're actually starting from the thinnest, zero material, and then ramping up to the thickest. In iMachining, we never do conventional cutting. We are always starting from thick and then going to thin. The other thing that happens with doing climb cutting is we want to keep a similar load on the tool and the spindle assembly such that the force acting on the tool is not oscillating. And this is important because every machine and every spindle has some flex in it. If we just stick an indicator on the tip of a tool and then just push on the tip of the tool, like physically with your hand, you'll see the indicator move, because in the end there is flex in the spindle and the bearings and the tool holder and everything. So what we don't want to have happen is an oscillation of the cutting force. Wherever the tool is pushing against, this is the vector of pressure, as this shows. This is where the cutting force is. So by sticking with climb cutting, we are keeping the force on the tool in this area. It's only ever pushing on this tool from this direction to down to this direction. Where if we were doing full slot cutting, you're actually getting the force coming down from this all the way back up to this side. So you're getting in full slot cutting, you're getting an oscillation of the force. The force is going bi-directional. At the beginning, it's going one way, and at the end, it's going in the complete opposite direction. We don't want that. We want the tool and machine to be flexed in one direction only. Chip thickness and chip load, are they the same? I think everybody, as we all know, if you go into the machinist handbook or you even look in a catalog, chip load. Chip load is generally what we see. We now see some manufacturers are now actually putting chip thickness in there. So what's the difference between chip load and chip thickness? So chip load is actually the thickness of the cut of the chip if we're cutting exactly at 90 degrees. Now at 90 degrees, chip thickness here and chip load are equal. When you cut less than 90 degrees, chip thickness and chip load are not the same. So remember, as I said, the tool is always going from the thickest part of the chip to the thinnest part of the chip at the very end. So as you can imagine, if we are only ever cutting down in this small section, let's say like only 30 degrees of the tool is cutting, you're never actually cutting the chip load that you want. And the end mill, it's made to take that chip load. We need to take a certain amount of cut to get the tool underneath the material, so that way we can actually shear it off. So as we see here in this right-hand picture, when we go to 40 degrees, to hold a constant chip thickness, we actually need to increase the chip load. So here is, let's say, another picture here. This kind of shows this is the step of the tool. At 10 degrees, the original chip load would be this distance here. So let's call it 0.1 millimeters, whatever it is. When iMachining adjusts the feed rate to hold a constant chip thickness, so that way the tool is actually biting enough material, the chip load actually, as you can see here, is almost like 2.5 times. So in iMachining, you're going to see that the feed rate is always adjusted such that the chip thickness is always the same. And 80 degrees is the maximum that we allow in iMachining. And here you can still see that chip load and chip thickness are pretty close to each other because we're near 90, but we're still doing that adjustment. Another major portion of trying to adjust for chip load and chip thickness is adjusting the feed rate based on the center of the tool versus the edge of the tool. So the CNC is commanded based on the center of the tool, but the tool is actually moving based on the edge. And I like to use the example of runners on a racetrack. So like when we see runners lined up on a racetrack, the inside person is actually staggered behind because it's the shortest distance. So we have the same thing here that happens with end mills. So what iMachining is doing is every time we see an arc, or even just successive points that make an arc, we are adjusting the feed rate such that the feed at the edge of the tool is giving us our correct chip thickness. It's kind of a crazy thing to kind of think about, that iMachining is doing both of those feed rate corrections. We are adjusting the feed rate for the engagement angle to get the proper chip thickness. But for arcs or any tool path or any successive curves of points that emulate an arc, we also need to increase or decrease the feed rate based on the edge of the cutter. So this means for internal corners, we actually slow down the feed rate so the chip thickness will be proper at the edge of the cutter. And when we do external corners, we increase the feed rate. So what does an iMachining toolpath look like? So a few things you're going to notice when you look at an iMachining toolpath is that we're going to have controlled step overs. So you're going to see that all the step overs are controlled and smooth from one another. You're always going to see exact stock machining. This means that you're not going to see toolpath that's cutting air. It's always going to start from the stock or the updated stock for that feature. And then the third thing you're always going to see is smooth motion. In the end, if you want to cut fast in the machine, you need smooth motion. We also want smooth load on the tool, so you're never going to see sharp changes of directions in an iMachining toolpath. It's always going to be smooth. Here's a simple bracket just to kind of show a couple examples of what it will look like. As I said, for closed pockets, you're generally going to see helical entry, unless we use pre-drilling or something. And you're always going to see kind of a morphing spiral, and you're going to see it, blends out to the shape of the pocket. But what you'll notice is iMachining with all of these shapes, they all start with a spiral, no matter what the pocket looks like. And then the tool forms the shape of the pocket after the spiral ends. Here's a little bit better detailed look of what does iMachining look like when you have a geometry that's a bit more complex. I mean, from my experience, most customer parts that we do see generally don't have lots of islands. It seems like electrical housings and things like that seem to be parts that have more islands in pockets. General machine shapes don't have islands from just personal experience and what we see. But when you run into islands, this is some of the unique things that you'll see with iMachining. So as I said, we will always start from a morphing spiral. And morphing spiral is important because, as I said, we want to keep the tool in contact all the time. So if we look down here, you're going to see that the passes are more tighter grouped together, and then you see the thickest or a wider spacing between these tool paths. So instead of the tool being repositioning all the time, we try to maximize morphing spirals. Once we hit an island, we do something called separation or moding, where we cut around the islands and we get those areas cleared out. Once islands are cleared out, then we return back to morphing spirals. So this is kind of the general goal of the toolpath. Spirals conquer islands, as you see here. So here we have a moat. So moat, just like moat the water around a castle. And then we go back to morphing spirals. And these are unique to iMachining. Only iMachining has morphing spirals and channels to separate regions. Now, as I said, the iMachining module is made up of two things: the toolpath and then the technology wizard. So you can have the best toolpath in the world, but in the end, for some given material and tool, we need to know what are the cutting parameters to drive it. So this falls back on us, the CNC CAM programmers. And what we see is that we have basically a pretty big problem. We have a lot of data that we need to take care of. We have the material, which is cutting speed, the hardness, the min and max step. We have the tool, which has a length, number of flutes, the helix angle, the chip thickness, the hardness. We have the geometry, which is the depth, and then we have the machine. What's the maximum spindle speed, the feed rate, the power of the spindle, and what's the memory size. So all these things are parameters that we have to take care of to figure out what is the proper feed and speed and cutting parameters. The technology wizard solves this entirely in that it takes out all that guesswork and trial and error, and it wraps everything up into one. So what this means is that we actually take in the material, the geometry, the tool, and the machine, and then what we give is we give depth, feed rate, step overs, and spindle speeds. And all of these things are perfectly synchronized to each other, and this is important. So this means when we do all of our feed rate adjustments and we have to figure out for a specific machine, if your machine can't hit a specific feed rate, well, then we need to adjust other parameters. So you can't just straight up say, hey, I'm gonna cut everything at 16th at the maximum spindle speed, and then I'm gonna run this chip thickness. Well, you might have such a big tool that you will run into you will run too fast for the machine to actually run the feed rate. So if that happens, you need to recalculate either your spindle speed, your depth of your width of cuts, your chip thickness, something. The iMachining wizard takes care of all of this. And the most unique thing about the iMachining wizard is we have a machining level slider. And in the end, we can't know and feel all of the particularities that is going on in the CNC. We don't know how strong a part is being held. We don't know what the fixturing is like. There are things that we can't know that we require human intelligence. This is why CAM automation and automatic programming of parts from a 2D drawing doesn't work. We still need our machinist background to be able to look at something and say, okay, I can run faster or I can run slower. So what we have is we have the iMachining slider. This goes from level 1 to level 8. And basically level 8 is the most aggressive, level 1 being the least aggressive, and then we have interpolated steps in between. And what this allows you to do is, most of our customers are cutting with level 6. You can jump right out of the software, run level 6, and you're good. But if you got like a really long tool and like a really long holder, like an extended holder, and you got some vibration problems and stuff because it's obviously extra long, you can lower the machining level. Or if you got a really good tool, if you got this thing held in a shrink fit holder, you can go faster. You can run towards machining level 8. And so this is the machining technology wizard, calculating all of these sets of data, and then you as the programmer sliding one way or the other, so using your intelligence based on what's happening at the CNC. The other thing we have is axial contact points, and this is a pretty big thing because this is kind of what gives us stability. I mean, this really is what gives us stability with deep cutting, and why deep cutting works so much better than shallow depth of cuts. So in this example, I love to talk about insert cutters with face milling. So when we have a big face mill and we cut across steel, every time the tool starts to enter in material, you hear the dunk, 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 dunk of the spindle and the tool entering in the material. And once the tool actually gets fully into the cut, you hear the spindle and all that clunking, it goes away. And I don't have a picture here, but I probably should because it would be great to show, but I think everybody knows it. When you look at the top of your part after a face mill runs across it, you see the swirl marks in the material is different at the beginning of the cut where the tool is trying to enter, and then after the tool enters, you have this smooth cut, and then at the end of the cut, when it exits again, you hear that dunk, dunk, dunk. So what happens is every time a flute is engaging and disengaging, remember I have my video with the plastic deformation, the spindle is flexing. Once you get more than 2 flutes in the material with a face mill, it smooths out the load and you're not getting that flexing anymore. Well, that same behavior happens with helical end mills. We have flutes, and based on the helix angle, we can actually get more than 1 flute in the material, And what this does is it adds stability. So in iMachining, we call these axial contact points. So here is one axial contact point over here. So for a 1/2 inch end mill at 45 degrees, you need to cut a depth of 340,314 to have one axial contact point. The deeper you go, the more axial contact points you get, the better it is. So this adds a stability to the spindle and the tool, so that way it's not banging around every time it enters and exits a cut. The stronger the machine, the better the tooling, the better the work holding, the less axial contact points actually mean something. So this is something you have to, understand. Okay, so let's get into some 2D iMachining programming real quick. In the end, my thing is about teaching us about the machining and what's going on, so that way we can appreciate when we actually do this iMachining 2D, why all our customers save money. Okay, now the presentation portion of this is for the live demo is actually pretty small. So I'm only going to put a couple tool paths down and talk about iMachining 2D and what we do. So I have this part here. I am going to add a 2D iMachining operation. I'm going to be using all of our feature recognition mode stuff. So for everybody who is familiar with iMachining, and you'll know that the feature recognition is something new that we came out with in the past couple years. And what this is we're able to just select simple features that we want to machine, and we automatically recognize the full machinable feature based on the tool, the stock, and everything. So I picked those two faces. I'm going to go select my end mill. And here we get a preview of what the machinable feature is. So what we see here is that even though I picked this face, the machinable feature knows that there's stock around this hole outside and we need to cut it. And we need to extend and come off of this wall. So normally we would have to create like a sketch or some type of geometry that we could pick. With the machinable feature, it does it automatically. The only thing I have to do is I say I just want to finish the wall. In my technology wizard, so here we have our slider that we talked about, so we can go from 1 to 7. If I go to a top-down view and zoom in here you can see how the engagement angle or cutting angle is actually changing between level 6 and level 6 and going down to level 1. So it gives you kind of a dynamic feedback, so we can see this before actually having to go out to the machine. And the only thing I need to do is I'm going to set my floor offset to 0. I will calculate my tool path. There's my tool path. I can disable my preview so I can kind of see what we get. So here you can see we have 2 depth of cuts. I will launch the simulation. I'm going to play the simulation in the external window just to make it a little bit less busy. So let's play. So as we see with iMachining, as I said, it's a controlled step over and it's working from the stock to the shape that you're cutting. And if we see down here, you can see the feed rate is constantly changing all the time. So every time the tool is entering and exiting the material, the feed rate is being adjusted for the chip thickness. And based on any internal or external corners, we are adjusting the feed rate based on the edge of the cutter compared to the center of the cutter. So here's a tool path. I can turn on the stock and target comparison. Okay, so we can see here that basically what we did is we finished the wall and we finished the floor. Most of the time now, I would copy and paste operations, but with iMachining's feature recognition, it's so easy to make toolpath from scratch. So I'm just going to make a new iMachining operation. I'm going to switch to working from the side because now what I want to do is I want to machine the side profile of this. Now in this case, if we look down, there's no floor or face for me to machine. So what we have is we have feature recognition by chains, And basically what we're doing is we are picking, turn off constancy. We are picking edges of the wall that we want to machine. And it's going to run the same feature recognition as it did for the floors. You can see the updated stock is being calculated because every operation is in the feature recognition is based off of the previous cuts. I'm going to finish the wall again. The only thing I need to do is pick my machining depth. So my machining depth was the default of the chain. If I would have picked the chain at the bottom, it would have defaulted to there. So here we see I picked the bottom, and let's go to a top-down view, and we will see the same thing that we saw before, which is even though I only picked these 3 lines, it made a complete region for me to machine, which we came off tangentially with an arc. We have this whole region that we need to cut because that's where the stock is. I'm just gonna put a small delta Z to go past the bottom. Once again, SolidCAM and iMachining is requiring that there is a programmer who knows what he wants to do. So as a machinist, I know when I cut this face, I want to bring the tool a little bit beyond the bottom because I don't want to bring the tip of the cutter right to the edge of the bottom surface. I want to extend it past. So you're still driving the software. You need to make those smart decisions. I'll calculate this tool path. So here we get our tool path. As I said, the technology wizard knows about the flute length, the depth of cut, and everything. So here we get one depth of cut. It did it automatically. In the previous operation, we didn't have enough flute length, so it automatically calculated 2 depth of cuts. I will switch back. I'll switch to the simulation just to see what we got. As we saw from the previous cut, stock-based machining. So what we see is the tool path is working from the stock and then machining away the material. If I turn on the stock and target comparison, we can see that we did a good job. We finished the line, we finished the arc, we got these faces. So now we got a couple different areas we could go to. We need to machine the slot, the hole. I'm not going to go through everything. I'm going to show cutting the outside of the part because there's some cool things I want to show there. So let's say we now want to machine around the outside of the part. Once again, I'm going to make a 2D operation from scratch. I'm not copying and pasting because this really shows how easy it is to make new operations. We're going to switch back to the top Mac position. We have a third feature recognition that's called outside. Almost every single part, we find that customers machine the outside of the part. So we have a dedicated feature recognition mode that's called just outside. And all we got to do is we're going to go pick the 1/2" end mill. And let's see, we got the depth there. We want to finish the wall. I will go and set my floor offset to 0 because there is actually no material we have to worry about there. And let's save and calculate this tool path. Now, what we see is we only get tool path over on the ends. And everybody's probably wondering, why is that? Well, our fixture's in the way. So if I turn on the fixture in SolidWorks, we can see here that this fixture is in the way of what we're trying to cut. And why is it in the way? Because I said I wanted to machine all the way down to the tip of the stock. And this could be what I wanted to do, but I want to machine around the entire part. So realistically, I only need to machine down from this face and go a little bit beyond. So what we're going to do is we're going to open up that operation. I'm going to change my pocket depth to be there. And I'm going to say, once again, I want to stay I want to go like 20 thou past. Now, when we see the geometry preview, we're still seeing that the tool is not going all the way around. Well, that is because in the fixture protection, we have 100,000, so 0.1, which is millimeter is like 3 millimeters, I believe, 3 or 4 millimeters. So there is a fixture collision protection of 3 millimeters. So this means it's actually protecting the tool based on the fixture over here. So I know I got a, the nice part here is I know I got a accurate fixture. This is a 5th axis fixture that is meant, the point of generally these 5-axis fixtures is to know good clearance around everything. So here, I know I can put like a 20th thou clearance distance, basically 0.5 millimeter. Now we calculate our tool path. Now we get the tool path all the way around the stock. As you can see, the upper level was also automatically calculated where the previous operation stopped machining. So I didn't have to figure out any of that stuff. We'll go to the simulation. Turn off the stock and target comparison and play it. And then here is our machining around the outside. And you can see this is just in the tolerancing of the cuts. That's less than 210. So I have some pretty tight tolerances in here for the updated stock. So as you can see with iMachining 2D, iMachining 2D is basically doing what we call prismatic features. They are planar floors and walls. They can have tapered, but they're no contour surfaces. Inside of our iMachining 2D, iMachining 2D is doing a combination of roughing. It can be doing rest roughing and finishing inside of one operation. So you can define whether you're finishing walls and floors. It is a multi-tool operation, which I didn't show here, but I think for any customers in SolidCAM, they're familiar with multi-tool. So you can define multiple tools to do separate finishing or to do separate rest roughing. And all of this is managed from the 2D iMachining toolpath. Go back to the presentation. Okay. Now I have kind of a challenge that I thought of, because from my side, as Emil said in the beginning, every customer of ours who cuts with iMachining would never give it up. It is something that it's almost like a magical experience the first time you cut with iMachining, because you're like, wow, I didn't know that my machine could remove material that way. I mean, to be honest, some of our customers, it removes material so fast that some of our customers have problems with the chip conveyors in their machines taking care of getting all the chips out of the machine. It seems crazy, but this is actually a problem that actually happens. So my challenge, and I mean, I think most of the people here are resellers in here, but for customers is run a test cut. This is the thing that will either show you that, wow, this is awesome, I can benefit from this, or you might go with it and be like, this is, I don't need that speed. I only make one part a day. I don't care about it. It's no big deal. But I can tell you that's not going to happen. So my challenge to you is run a test cut. And I got some simple steps here for what you should do. Go in your shop, find a block of material. So you just need some chunk of material. It doesn't matter if it's aluminum, steel, whatever. Find a chunk of material. And then what you want to do is you want to go to matweb.com for material web. And so you can just go to Google, type Matweb. This is an online material database. And what you do is up here in the top, you just need to type what material you got. So I'm just going to type in 7075 just for instance. It gives you a list of materials. This website has everything in it. You can go to, let's say, 7075 T6. And the only thing we need is the ultimate tensile strength. So for English units, this is 83,000 PSI, and for metric, it's 572 megapascals. So you are going to find your block of material, go on Matweb, get the ultimate tensile strength. This is going to be used to create an iMachining database. I'll show you in a minute. Find a new 3 or 5 flute solid carbide end mill in your shop. Get something in the 6 to 10 millimeter range. I say this because the larger tools you go, the stronger your machine has to be, the fixturing has to be. So the last thing you want to do is go, not hold on to something too tight and then have your part fly out of your vise. So 6 to 10 millimeters, that's like 1/4 inch to 3/8 end mill. It's a nice size to start. Then you want to use a caliper, so you can measure 1 or 2 axial contact points. So this is that depth here. Model a simple rectangular open pocket as you see down here. You can go with these standard parameters, but it doesn't really matter. You can make the width like 6 times the diameter, the length or to be 4 times the diameter, and make the depth either 1 or 2 ACPs, depending upon how much flute length you got. Program a simple iMachining 2D pocket using level 6. If you don't have iMachining today, call up your reseller, ask for just a trial license of it. You just want to make simple 2D iMachining. You saw how simple it was. Pick level 6, go cut it on your CNC. You're going to be amazed. Then, if you further like, you can experiment with some faster cutting. So if you have additional blocks of material, or maybe your block is thick enough that you can actually rotate the block, in this pocket, it was kind of, you can see we could rotate the block and cut another shape on the other side. To experiment with faster machining, you can switch to level 8. And then there's also a turbo mode, which is an easy way to go even extra faster. And then there is a machinable factor in the material database. All right, now I'm going to show real quick what we need to do. So you go to Matweb, you find your block of material, you find your ultimate tensile strength, it's 572. Let's just close this part. So you need to go to the iMachining database. If you know it's an aluminum, you're just going to right click, say new material. In the new material, you can see here I have 7075 T6. All you need to do is type in the ultimate tensile strength right here. So if I were to say new material here, you can see the only thing we need to do is type in the ultimate tensile strength. I'm in inches at the moment, so it would be 83,000, and that would be the ultimate tensile strength. That's all you need to do for the material. And then if you're not set up with machines, what you can do is underneath of machine database where it says defined by VMID, make a new machine and just call it, you can just call it global. And if it's underneath of this defined by VMID, we automatically take the spindle speeds and feed rates directly from the VMID. Generally, these are going to be the maximums of your machine. So like if you have a 24,000 RPM spindle, the maximum spindle speed is going to be 24,000 RPMs. And if your maximum feed rates is, 2 meters a minute, you're going to have that in there. Now, what we find is not every customer wants to be machining all the time. So at the maximum of their machine. So a lot of customers will set up separate feeds and separate machine that actually has a specific maximum RPM. Like I said, if you have a 24,000 RPM spindle, not everybody is running 24,000 RPMs all the time. They sometimes cut it down to like 18,000 or 20,000 RPM, so you can do that. But the simple thing is create a machine defined by VMID and then use global. So you make your machine, you make your material, model your block that you got, make this simple open pocket. So simple open pocket, just your width, your length, your depth. I'm going to walk you through how easy this is in iMachining because it can't, setting this up is nothing more than a few minutes of your time. And it's a pretty exciting, eye-opening thing. So we're going to go grab our, let's grab my Haas SS. Let's go put down a coordinate system real quick. Obviously, you need to put your coordinate system where you're going to pick up your part at. So for the stock, in this example, we're start with a machine block that is the same size. So you can put zeros in all of your box. So this way you get a stock that's exactly that size. An important thing to note, make sure your stock is actually the proper size. So like the last thing you want here, if this is some like solid edge in your machine, and you know this thing is varying by like, I don't know, a 0.5 millimeter or 1 millimeter because it's a solid edge, machine that edge and make it square, because the toolpath does, you know, it's managing the engagement angle, so we need that to be accurate. And this is one thing that sometimes people forget to do. So in your machine database, as I said, you should have a global one. So make a global machine, and we can pick our 7075. I can pick level 6 because that's what I said to do. Really simple, 2D iMachining. Use feature recognition by faces. All you got to do is pick on that face. I will make my tool. So in this case, I don't know, 375. Make sure you know your helical angle, so you enter it there. We've modeled that you measured with a caliper what the axial contact point is, so we'll just pick 4 flutes. There's our feature. You don't have to worry about finishing the walls and the floors. If you like, you know, you can set the floor offset to 0, and then calculate toolpath. That's simple. Go take this out the machine. Go take this out to the machine and run the test cut. The other nice thing with cutting with smaller tools is with the smaller tools, you're going to have a little less feed rate than with the larger tools. So this is, I mean, when you start cutting with a big tool and you start cutting fast, the feed rates are pretty, I'm not going to say scary, but if you're not used to cutting that fast, it's a little shocking. With the smaller tools, the feed rates are more, you know, you're not running anything super crazy where the machine's moving around so fast you can't even see what it's doing. So G-code this and then run it. And then if it works, great, and you're like, man, I want to see how far my machine can go, you can change the slider position up to level 8. In this modify cutting conditions page, as I said, you can activate turbo mode. Turbo mode will basically you know, run higher surface footages, bigger chip thicknesses, and will use more power of the spindle. It's usually a pretty big leap. If you're in aluminum, you're not going to see as big a leap, but in steel, you'll see a pretty big leap when you go from turbo to non-turbo. And then the last thing that you may want to do is inside of the iMachining database, the one that you created. Let's go to that 7075. You have a machinability factor. And basically what you can say is, you know, some materials, the ultimate tensile strength is not the only thing that decides how machinable it is. Like titanium is more abrasive to the tool, so like it wears faster. So titanium would be something that would be less machinable based on a similar material with that hardness. So machinability factor, if you want to go faster, you can say it's more machinable. So 50% will allow it to be more machinable. So that ends my presentation on that. And then the last thing I want to end with, because I think this kind of says a lot, is this last video, and I'm going to switch back to the GoToMeeting to play this video.
My hopes is that not too many people learn about iMachining, because it is my biggest competitive edge.
Okay, so as Greg Burns said there, iMachining is his best competitive edge. It is the truth. As I said, it is like getting multiple CNCs for the price of one, and it truly will change the way you machine parts. Okay, I will switch back to my screen. And that concludes the presentation. So let me see if there's any, see if there were any questions. So if anybody has any questions, you can feel free to type it in the list. Okay. Poll questions. Okay. What do we got? Will they record? Yes. So a couple people said they missed the beginning of either they missed the beginning or if this is recorded. Yes, all of our presentations are recorded and they will be. You'll get a link for that. Does iMachining consider the quality of the end mill? So what we have with the quality of the end mill is that you can define the material of the tool, whether it's high-speed steel, cobalt, carbide, or premium carbide. And so basically what these do is it's basically saying, what is the quality of the tool? So if it's a good quality tool, you can obviously cut faster and it's going to handle things better. In the tool definition, you can also explicitly define a specific machining level and also a chip thickness for a tool. Because one thing that is generally true with higher quality tools is higher quality tools can machine faster, so the machining level can generally be higher, but higher quality tools can also have a bigger chip thickness. Conversely, you can have a tool that is set up that maybe can only handle a small chip thickness. So yes, we do consider the quality of the end mill. You just have to kind of define in the SolidCAM tool table some specific things about the tool, like the material, and then you can also override the machining level. Can you send a part with the fixture? Absolutely. Can you send a part along with the fixture? Yes. For the webinar, I will have whenever we do all the webinars, all the part files and everything will be included for resellers and everything. I'll also have all the videos that I use, so the plastic deformation video, because seriously, the plastic deformation video is one of the coolest videos to talk to customers about, because like, I mean, really when you see what is going on with the tool shearing away the material, like it really is, I'm not gonna say it's an eye opener, but it really opens up that discussion about, okay, so this really is what happens down at the details of the cutting, and those details are what iMachining manages, and we manage it automatically from our side. How do you calculate machinability factor? I don't have a specific, there isn't like a specific thing for machinability factor. The machinability factor really was something that was, this was a request from some of our customers through the years. Like it also runs into even customers, or like different machines and how different people want to run. So like some people are all about, man, they're trying to push things as fast as they can, and other people like to bring it down a little bit. So the machinability factor, there isn't some rule. It's an experience thing. I mean, in aluminum, I generally know I can increase the machinability factor because it's aluminum. For the most part in aluminum, you don't really run into a limitation of what the tool can do. You run into a machine limitation. You run out of horsepower, or you just can't move the machine any faster. So in aluminum, you can, man, even these smaller tools, you can push them to like the maximum and you still won't break them. Of course, once you get into long tools, then you end up with more chance of breaking. But so the machinability factor, it's kind of a pretty much I'm not going to say trial and error, but a little bit of an experience thing. How effective is iMachining for super alloys like Inconel? Amazing. Seriously, this is, people who cut with super alloys with iMachining are just blown away, because one of the biggest things with like super alloys and those things is it destroys end mills. It destroys tools. So it's not so, Inconel, you can cut it, but it just destroys tools. iMachining, and the thing with, you know, those materials that I talked about, they're abrasive. They really wear the cutting edge of the tool down. And once that cutting edge of the tool wears down, the tool just stops. So what I would say is that the harder the material, the tougher it is, the iMachining makes the bigger benefit. You know, in aluminum, for sure, we cut faster. When not using, you know, when using super alloys and stuff, the benefits, it's magnified, really. Style foam model, I don't know what that is. I'll have to search. Is there a formula for machining factor? I think that's so funny. Again, a couple questions with the machinability factor. No, there is no. So the machinability factor, trial and so it's funny how many people are asking about this. Trial and error. You know, you should. I mean, generally, you know, if a material is a more easy or harder to machine material, but generally, I wouldn't tell any customer to touch the machinability factor until you go do cuts on the machine, because in the end, you have to know how your machine's working, with your tool holders working. There's definitely a difference between a customer who's going to have, you know, a high quality machine that's brand new with scales, with shrink fit tooling and like the best things. That machining setup is different than if you bought a machine or you have a machine that's 15 years old and you're using, you know, solid end mill holders with, you know, with a welding shank and a nut to hold it in there. So there is a difference there. So these are things I can't know and SolidCAM can't know. So these are things that you have to experiment with. As resellers, I would say our resellers that cut with iMachining, they know they have experience. Just like I said with aluminum, I know I just increase the machinability factor right off the bat because I know I can. So a little bit of trial and error, but you always want to just go make that first cut. And for sure, that first cut is always going to be faster than traditional cutting. Hands down, it's always going to be faster. So it's always easier to go faster than it is to go slower. And the other side of the machinability factor is it can go into what was I going to say? Tool wear. So, you know, you can lower the machinability factor to get increased tool life as well. And that's something, you know, some customers are happy replacing a tool every part, and other customers really want to, you know, I know customers where sometimes the tooling cost is more money than the machine time, you know, because most customers are charging, you know, somewhere in that $60 to $120 per hour machine time. That's the price of end mills. So if you're cutting, you know, if that end mill is only lasting one part, and your one part only takes 20 minutes or half an hour to cut, your end mill costs are larger than your machining time. So this is something customers also have to, you know, decide for themselves when using iMachining. Do you want to try to cut a little bit faster, to have faster cycle time, or do you want to try to extend the tool life, because the tool life is more important? And iMachining with insert cutters. Yes, iMachining works with insert cutters. We have the thing with insert cutters is there are more particularities with insert cutters than there are with helical end mills. Insert cutters can be very inaccurately built things where the differences between one flute to the next are larger, and this equates to bigger vibrations and uneven cutting forces. So we have specific tools that we've done cutting with this car, and I forget somebody else. We have a couple tools, and our experience with using insert cutters is when you have a good machine that can hold the tool into the cut, and you have a proper insert cutter, like a porcupine cutter, where all the inserts are accurate in the holder, you get amazing benefits with iMachining. But a lot of times what we see with standard people, using insert cutters is they're thinking, oh, they're buying inexpensive inserts, inexpensive insert holders, the tools, and they kind of have a weak machine, and the machine is just not able to do deep depth of cuts and keep the tool in the spindle, to keep the tool in the material. So with insert cutters, it's a little bit more tricky because you got to have the right tooling with the right machines and the right setup. Where with helical end, with carbide end mills, you don't have that same problem. They're, all the tools are ground, the tools are good, the accuracy of the tools are good. You get a very similar result for all carbide end mills. The better tools just cut faster, last longer, have better reliefs, but it's not a matter of, it's generally not a matter of, oh, this tool won't work for this material. It's a matter of how fast you can go and what the tool life is. When it comes to insert cutters, there's more variables to contend with. And I think that is it. So, okay, thank you everybody for joining the meeting. Next week, I am doing basically the same, not the same webinar, but we're doing it for iMachining 3D. So for people that are more interested in iMachining 3D, I will be covering the same stuff I did in the beginning section, but then I'm going to be going over iMachining 3D and how iMachining 3D can be used for contoured parts and molds, and how it combines everything from roughing, rest roughing, and semi-finish into one toolpath. Because for as amazing as iMachining 2D toolpath is, most of our customers who use iMachining 3D see even larger cycle time benefits in iMachining 3D, because we reduce some of the other traditional rest roughing and semi-finished toolpaths. So you get all that combined in one. So the next toolpath, the next presentation is a really, really good one too. So great, thank you everybody. Have a good day and hope to see you next week. Bye.